Okay, welcome everybody to the April 11th installment of the California Dreams Technical Series. Today we are very glad to have Jonathan Klamkin with us. Jonathan is a professor at the University of California, Santa Barbara, where he's been since 2015. Before that, he held technical staff appointments at MIT Lincoln Lab, was also at several other universities. He's published over 250 journal and conference papers, lots of patents. He is not only a faculty member, but an entrepreneur. We were lucky to have him as one of the very early participants in the formation of the California Dreams Hub. Jonathan is also the director of the Nanofab Lab at UCSB, which is really one of our flagship nanofab labs throughout the country, and it's contributed so much important work, as you heard in talks from Umesh and others throughout this series. Jonathan's also the recipient of awards such as the NASA Early Career Faculty Award, DARPA Young Faculty Award, DARPA Directors Fellowship, etc., and a Fellow of Optica. So welcome, Jonathan. Please take it away.
Thanks, Steve. Thanks a lot for the intro. Thanks, everyone, for joining. I think, as you know, if you saw the announcement, the title of the seminar is Integrated Photonics. It's always about high performance. I'll share a few thoughts on that during the presentation. So here's a brief outline. I'll give a little bit of background, very briefly talk about UCSB and the Nanofab, and you have probably heard about our facility in other seminars and likely will in future seminars. Give a little bit of background on what photonic integrated circuits are, and then highlight an application of PICs, optical interconnects for AI infrastructure, that has gained lots of interest, especially recently, over the years, but especially recently after NVIDIA made some announcements at their flagship GTC conference. And then I'll focus on heterogeneous integration of 3-5 materials on silicon in support of silicon photonics for optical interconnects, but also for a few other things, and touch on scaling and commercialization opportunities. So very briefly, I'd be remiss to not mention the facility where we do a lot of this sort of fundamental device fabrication work, the UCSB Nanofab. For those not familiar, the Nanofab is an advanced nanofabrication user facility. We like to refer to it as a user facility because it is an open access facility. Users are not only internal UCSB faculty, students, researchers, but also external. We have users from other universities, government labs, and many from industry. So it's a big part of sort of the startup ecosystem in Santa Barbara and Southern California. Facility houses about $60 million worth of equipment and has been in operation on paper for more than 25 years, in its current location, probably 18 or 19 years. And why it was developed? Well, it happened over time, but it's really been there to support innovation. We've got a user base that approaches 600 annual users, and about half of those actually are users from industry, from companies. And to our knowledge, this is the largest industrial base supported by any university nanofab facility, maybe in the world. I say United States there. We operate by charging user fees, different rates for academics, industrial users, and that's how we sort of fund our operation. When questions like what kind of capabilities do you have started coming up in the context of the CHIPS Act, we defined our facility as a greater than or equal to 100 millimeter facility. Many of what we do is on small pieces, small wafers up to 100 millimeter or 4-inch. But many of the tools also support up to 150 millimeter wafers, and we have maybe 1 or 2 tools that could even take a 200 millimeter wafer. I won't go through the details on the type of equipment that's in the facility, but encourage you to visit our homepage where you could see sort of a detailed list of equipment. And if you're interested, there's lots of contact information on the website if you'd like to work with our staff or get access to the facility. This slide just gives an idea of some of the research areas leveraged for UCSB research. And there's sort of a concentration We do plenty of silicon work, but lots of non-silicon work, especially with compound semiconductors and 3-5 materials. And the research spans electronics, photonics, MEMS, microfluidics, material science, physics, chem, bio, and quantum. And you can see some nice images of things that have been built in our facility and sort of the scale of those structures, devices, and very small structures. Last couple of things, if you just think about the impact of the facility, we like to show this slide to show where users come from. So in terms of state impact, our hub is based in Southern California, so that's important to us. This facility has been accessed by more than 200 California companies since 2006, 260 companies across the country. Almost 200 of the companies that have accessed our facility are small businesses. Active companies, about 68 are local in Goleta and Santa Barbara area. Almost half of those were started and led by UCSB faculty or graduates, and approaching 100 academic institutions since 2006, really just showing impact across the country and state, but occasionally we have users from other countries that work with our staff to do fab development. And it has had an impact on the sort of startup economy and ecosystem in our area. These are a few examples of industrial users and their commercialization successes. So mostly recent things. A highlight I'd like to point to is Google AI. So a lot of the Google quantum AI chips that we hear about in the news were actually developed and built at the UCSB Nanofab. And it was only recently in the last year or two that Google built out their own facility to sort of scale up for production. And that's still local. They have a very strong presence in our area. A number of other companies, SLD Laser, just to give some examples, is a gallium nitride laser company that was acquired a few years ago by Kyocera. Illuma, I'll talk a little bit about later. That's a company I started about four years ago that actually went public and is listed on NASDAQ now as of a couple of weeks ago, and has a lot of commercialization traction. Freedom Photonics is a photonic integrated circuits and laser company that was acquired by Luminar, which is an automotive LiDAR company. Transform, you heard a bit about GaN power and RF electronics from Umesh a few weeks back. Transform was recently acquired by Renesas, and Crystal and Mirror Solutions was acquired by Thor Labs. They build these very low noise semiconductor-based super mirrors that are used in lots of experiments and spectroscopy applications. So many of these companies developed processes at the UCSB Nanofab and then either transferred those processes to industrial foundries or to their own fabs that they ended up building as they started to commercialize their technologies. So a bit of background on photonic integrated circuits. I think many of you are aware of what these are. It's primarily a single chip that integrates lots of optical functions like lasers or optical amplifiers, optical modulators, detectors, passive elements, filters, and things of that nature on a single chip. So analogous to electronic ICs, but not quite as mature. There are lots of flavors, different platforms. Some of these are based on compound semiconductors. Some of these rely on silicon photonics as the base. So a little bit like in the electronics world where you might have SOI, FD-SOI, BiCMOS, and things like that. Not quite at that maturity level, but maturing. Some PICs have a few optical functions on a chip, and there's a big benefit. Even the very simple thing like a laser modulator is beneficial over having two separately packaged devices, a laser modulator that then have to be separately packaged and fiber coupled. Some PICs have hundreds and thousands and tens of thousands of components. So not quite, billions or trillions like we have in the transistor IC world, but still quite complex compared to when people first built laser diodes on semiconductor chips. A few applications, and some of these I'll touch on a little bit later, but integrated photonics, photonic integrated circuits, were initially envisioned and developed really for telecom in the early days to integrate, for example, multiple wavelength lasers on a chip to support WDM applications or components for coherent receivers and coherent transceivers. when coherent was being pursued for long haul. And there were substantial benefits to integrating multiple wavelength lasers or making tunable lasers on chips for performance reasons, for in most cases for reducing cost, size, weight, and power. But the other benefit you see when you integrate these components on a single chip is an increase in performance, things that you really can't do when you build a photonic system from discrete components, and I'll touch on some of those. And datacom persists. I'll come back to this later. So transceivers for shorter reach interconnects, because data transfer is a little bit different now. Lots of data moving over shorter distances relative to, say, a decade or two ago. PICs are also used for other things like beam steering, building optical phased arrays that can shape and steer a beam, that can be used for sensing, could be used for depth perception, is used, for example, in navigation and docking. RF photonics, this is an example of a photonic integrated circuit we built to generate and distribute millimeter wave signals for RF applications. A very neat way to use optical true time delay instead of RF phase shifters to be able to tune the carrier frequency for millimeter wave signals. That was the first time that had ever been done for millimeter waves. And we did that with a fairly simple low-loss silicon nitride PIC platform. Laser comm, using lasers for free space communications. This is prevalent now in space, not only supported by space agencies such as NASA and the European Space Agency, but also commercially, companies that are deploying laser comm systems. And I'll talk a little bit about sensing in the next slide. PICs are also being used in computing, optical computing. That is a real thing that, again, is not only in research, but being pursued by companies, and is also being leveraged for quantum photonics applications, for doing things like generating entangled photon pairs. So for quantum photonics, you need other functions that maybe are a little different than the traditional functions that are used in datacom and telecom. And lastly, using interconnects for array-based systems. This is something that we've been pursuing in California Dreams with some of our hub partners. So similar to the types of wideband transceivers that are built for, say, datacom, but maybe slightly geared toward other applications, like taking lots of information off of focal plane arrays or from RF phased arrays and transferring to another place. You could use silicon photonics, for example, for doing that. And just coming back for a moment, what was the purpose of the title for photonics? What I'd like to say is that meeting performance specifications has always been a higher priority than achieving low cost. I think we did ourselves a disservice 10, 15, 20 years ago when we said, hey, the reason we're pursuing silicon photonics is for low cost. Anyone that's tried to work with a silicon photonics foundry, even at scale, would be the first to tell you that silicon photonics is not cheap. It's very expensive to run full silicon photonics wafers at foundries. That might come down over time, but we don't really do this for low cost. We do it because performance requirements for a lot of these applications, even what we would consider a volume application like data centers, are extremely stringent. Having lasers that are very stable over temperature and meet requirements, these are not very simple things to do. So all I'd like to say here in summary is that we didn't go to silicon as opposed to compound semis for photonics to get to low cost. It was really about having very stable, high yield processes and being able to achieve the performance requirements for a lot of these applications. So a couple other examples on PICs. And after this slide, I'm really just going to focus on silicon photonics and silicon systems and integrating 3.5s. But photonic integrated circuits also come in 3.5 platforms, indium phosphide, gallium arsenide. The example on the top is an indium phosphide PIC that we developed for atmospheric gas sensing. This is a PIC that integrates two fairly stable and tunable lasers, phase modulators, detectors, and a number of passive elements to detect in this case, carbon dioxide in the atmosphere. It's a technology to be developed with NASA that is now going through steps to package for space qualification with an industrial partner. And that could be extended to other wavelengths for other gas species like methane, for example. This example on the lower left is also an indium phosphide PIC that we developed for FMCW LiDAR that has both a transmitter and receiver for that application. This one in the lower middle is a gallium arsenide optical phased array, has phase modulators and optical gain on chip that could be used for a number of applications, but this specific application was for industrial machining applications. And the last one, a widely tunable 1030 nanometer PIC that we developed for topographical LiDAR that was also done in collaboration with NASA. I mentioned earlier that data transfer is a little bit different than it was a couple of decades ago. Once upon a time, we really only cared about long haul. What's happening now is that optical interconnects are making their way into shorter and shorter reach applications, data center interconnects, inside data centers, between data centers, even few meter, and people are considering optical for even centimeter reach, for example, to interconnect, let's say GPUs with high bandwidth memory. People are really thinking about doing that with optical, even if it's only a few centimeters away, because there's a bit of a bottleneck there. And a lot of what's happening today for these short reach interconnects is in support of AI infrastructure. Indium phosphide is still widely used. You can integrate lots of transmitters and receivers on indium phosphide chips, but silicon photonics is really sort of coming to the forefront. And I'll just briefly mention the differences between these platforms. It really comes down to whether or not you can monolithically integrate a laser, optical gain to overcome losses on the chip, or the actual laser that drives those transceiver circuits, and substrate size. These are the substrate sizes in millimeters that are common for these platforms. So we didn't go to silicon photonics, again, coming back to that point, to scale necessarily just for large volumes. It does have to do with performance. You can make much lower loss waveguides, for example, in silicon photonics, because of the type of tooling you have access to on 200 and 300 millimeter wafers. You don't have access to that tooling, and it's not just lithography, it's how you do packaging and other things. You don't have access to those technologies for these other materials and other substrate sizes. So some of you might have watched the NVIDIA GTC conference. I didn't watch the videos, I hope to soon, but I did read a lot of the articles, and there was a huge buzz about silicon photonics again after some of the announcements that were made at that conference. Many of us in the field have known NVIDIA has been working on silicon photonics and this supply chain for a few years now, but it was a surprise to many people that they'd been doing this. I think it's the first time they really talked about this publicly. And one point that I'll make, this is from a little bit earlier this year, in an article that says NVIDIA CEO believes AI has to do 100 times more computation now than when ChatGPT was first released. And when I see an article like that, I take that to mean lots of power consumption. And one of the bottlenecks in the power consumption has become the interconnect. And what's happened in the industry, this is a slide from TSMC, that is NVIDIA's silicon photonics fab partner, is that years ago, sort of mega data centers really needed lower cost and maybe different pluggable optics transceivers. And this is all normalized to the amount of power that those pluggable transceivers consumes, and latency. Doesn't really mention cost here, but that's of course important, especially if you're looking to plug in 32 of these pluggable modules into a tray in a rack. And then there was a transition to co-packaged optics where silicon photonics transceivers started to get integrated nearby, near, say, a switch ASIC. And doing that instead of using pluggables could reduce power and latency quite a bit. And now what's happening is, for a lot of these AI applications, you have things like GPUs and XPUs closely integrated on, in some cases, the same substrate package, whether that be silicon or glass or something else. and closely integrated with the silicon photonics transceivers to get the data on and off of those packages. And here just sort of shows the benefits to doing that when it comes to power and latency. And then this slide from NVIDIA's presentation gave an idea of what that looks like. There's the co-packaged optics inside. The supply chain that they've developed out, you can see how complicated the supply chain is. And one thing I'll point out is that the laser module that's feeding this in this particular picture seems to be integrated in a separate pluggable package. So it takes one of those interfaces to package the laser source that's feeding the silicon photonics inside that package. So, right, so this is the bottleneck. Need wide bandwidth, low latency, and energy efficient optical interconnect. So the interconnect is a big fraction of the overall power budget. Okay, so talking about technology platforms again. So silicon photonics has a lot of the components that we need. Active components like silicon-based modulators, germanium detectors, and other things. But to date, laser and optical gain functionalities are not monolithic. Silicon photonics is already widely deployed for telecom and datacom, but is in higher demand now, especially because of things like co-packaged optics that I just mentioned. But people are hoping to use silicon photonics for other things as well. And the rest of the talk is going to focus a bit on heterogeneous integration and especially how to integrate lasers and gain material. This is how it's done today. Co-packaging. In some cases, even in pluggable optics modules, companies would integrate silicon photonics chips with laser chips sort of side by side. And in some cases, there was even just a short fiber coupling the light from one chip to the other. In some cases, the chips are sort of butt packaged and light is butt coupled from one chip to another. In some cases, the lasers are flip chip integrated. And that works reasonably well, but is limited in scalability and in most cases requires very precise alignment. So a little bit too much cost in the assembly and packaging, which is really not what you want. That's the beauty of silicon manufacturing. All of the cost is in the wafer fab, and packaging and integration and even test is very standardized. That's how you reduce cost ultimately in the semiconductor world. Another approach that is deployed commercially, this is the approach that Intel commercialized, bonding 3-5 materials directly onto SOI silicon photonics. And what they do typically is bond coupons, sort of thinned indium phosphide wafers, maybe 100 micron thick coupons are bonded, the substrate's removed, and then the lasers are sort of fabricated on the silicon wafers, and light evanescently couples between the silicon waveguide and the 3-5 material so that the optical mode can experience gain. That's commercialized. I believe the numbers Intel likes to share is that they've shipped something like 8 million transceivers, and each of those transceivers had 8 lasers, so 32 million lasers have been deployed and are in operation in the field. So this technology works very well. Another technology, which I think is just really an incremental improvement over that, is to leverage micro transfer printing, whereby instead of bonding sort of full thickness coupons that then need most of the substrate to be removed, you could transfer thin film coupons. You have sort of a sacrificial etch layer that allows you to batch transfer many thin film coupons from native substrates like indium phosphide or gallium arsenide onto silicon. That's something we've worked on quite a bit as well. Again, that works, but I see it sort of just as an interim sort of incremental improvement over the coupons. What seems to be catching a lot of attention is doing direct growth of 3-5s on silicon, and that's what I'm going to spend some time focusing on for most of the remainder of the talk. The reason this is attractive is because you can integrate many gain elements. So what we refer to as gain density per die can be very large. This is potentially front-end compatible. So imagine a CMOS facility taking in an MOCVD tool or so to do the deposition in-house. They do this already with germanium deposition, selective germanium growth to integrate detectors for silicon photonics and for doing silicon germanium by CMOS. So why not take another CVD tool that can deposit these materials and just do it right in the front end line. These other techniques require wafers to go out to other facilities in many cases, and either then to go to a back end fab line or come back into the process. And cost could be potentially low. If you can directly grow the 3.5s on silicon, there is no 3.5 substrate. And you're eliminating a lot of that sort of assembly cost to put, either thin film coupons or chiplets onto the substrate. If you only need one coupon or one chiplet, that's totally fine. But if you ideally want many gain elements per die, you can see how it gets very expensive to populate the wafers in either of these cases. So let's talk a little bit about direct heteroepitaxy on silicon. This is not an easy thing to do. People have been working on this on and off, and even in theory for decades. When we typically present the work that we've been doing to people that haven't been following specifically what we're doing, usually we just hear things like, oh, this doesn't work. People have tried, what are you doing that's any different? I would say the only thing we've done that's different is we've been working on this now for a decade, literally 10 years persistently, from the early days of AIM Photonics, when AIM Photonics first started. And we're pursuing this technology for different applications, for devices that are a little easier in terms of material quality requirements. I'm going to mostly talk about lasers, but later talk a little bit about detectors, a very simple two-terminal device that doesn't draw a lot of current, so it's kind of inherently reliable. Whereas when people first pursued 3.5 on silicon, they were thinking about transistors, and they were competing with silicon. I don't think that was the right application to start with in pursuing this technology. So lots of challenges to overcome. These materials are very lattice mismatched. There's a significant difference in the coefficient of thermal expansion of these materials. Some people refer to this as a polarity mismatch, where you're growing a binary material on a monosilicon material that induces anti-phase domains. Things don't quite match up. It's another source of material defects. And there's lots of things that we've done over time to sort of overcome and mitigate some of these issues. And I'll touch on some of those. Before I do, just also touch on quantum dot lasers. Why is there a strong renewed interest in quantum dot lasers? Well, quantum dots have also been around for a very long time, and not quite as commercialized as quantum well lasers, but there are inherent benefits of quantum dots, not just generally if you need a good, reliable, and efficient laser source, but especially if you're trying to integrate lasers on other platforms, whether you're butt coupling the lasers, wafer bonding the lasers, or directly growing the lasers on silicon, which is primarily what we're doing. Generally speaking, quantum dot lasers lend themselves to lower threshold, higher differential gain, higher temperature stability. Carriers are much more highly confined in quantum dots than they are in quantum wells. Line width enhancement factor is lower, which lends itself to lower noise, higher narrower line width lasers. Because of that, these lasers are less sensitive to optical feedback, more so than, say, quantum well counterparts. And you can do things like modulation doping, which also improve laser performance. Another very important benefit is that quantum dots are more tolerant to poor material quality, to dislocations. There's a sort of cartoon picture here showing what happens when maybe a threading dislocation makes its way through a few layers of quantum wells. Well, carrier migration lengths are fairly long in quantum wells. The confinement is not quite as strong as it is in quantum dots. And so carriers migrate to those defects and recombine non-radiatively. So that's a big issue. These quantum well lasers with lots of defects are inherently unreliable and lower efficiency. Instead, when you have, let's say, a thread making its way to or through a few layers of dots, in some cases, the dots actually trap that defect, so prevent it from going through other layers. And the carrier migration lengths are a lot shorter. So carriers might be migrating over here, but they get trapped in the dots. And so non-radiative recombination, because of that material defect, is a lot lower in quantum dot lasers. And my colleague John Bowers and his group has published a lot of good papers showing that not only do these lasers work, but they can be very reliable. And so a number of papers out there, we can look at the reliability of these lasers as the material quality has improved over time, but also because of using quantum dots instead of quantum wells. And the reliability is approaching that of the reliability on native substrates like gallium arsenide. So how do you do this? There's a few different approaches. In all cases, you have to start with CVD or MOCVD. You can't really grow or nucleate, let's say, gallium arsenide directly on silicon without doing, let's say by MBE, without doing something else first. And in many cases, what people have done traditionally is use miscut substrates, very grossly miscut silicon substrates, 4 degrees, but really like 6 degrees and 10 degrees. And in many cases, what they've done is, this is one example where it was done on axis, grown germanium by CVD first. And then once you have a buffer and you can transition to gallium arsenide from germanium, because the lattice constant is fairly similar between gas and germanium, you still have the polarity mismatch issue. Then you could grow, let's say, a laser stack by MBE. And there've been some nice demonstrations where that was done, and reasonable performance quantum dot lasers demonstrated on silicon. This is a technique in the middle that we've approached over time, growing the initial buffer by MOCVD, fairly thick buffer with a sophisticated means to filter and sort of trap defects, and then switch over to MBE to grow quantum dots. And why the switch? Because people tend to think that you need MBE to grow quantum dots, and if we want access to quantum dots for this robustness to material defects, then we've got to do this sort of hybrid approach, MOCVD plus MBE. Then there's the all MOCVD approach that we've been working on, one of the few, if not only groups that's been doing this. If you can grow the whole stack by MOCVD, why not do that? MOCVD is sort of the industry standard for production. You grow very high quality material by MOCVD. So we've come up with techniques to grow not only the buffer, the initial nucleation on CMOS compatible silicon, but also to grow the quantum dots. You can grow quantum dots by MOCVD. It just hasn't been as common, but I'll show you some results later where our quantum dot lasers are as good or better than MBE quantum dot lasers. So how do we grow the initial buffer? There's a number of ways to do this. One technique that we really like is we take the CMOS compatible silicon and we sort of treat the surface in various ways. In this particular case, we pattern lines of silicon dioxide so that we can use very mature chemical etching that's used in MEMS processes to form these nano V grooves. And we do that so we can expose the 1-1-1 interfaces. This is a way to mitigate or trap those anti-phase domains that are inherent when you grow polarity mismatched material on silicon. And what happens is a lot of those anti-phase domains either don't form or form but get trapped really close to this 3,5 silicon interface. And then on top of that, after doing the initial nucleation and starting to planarize the growth, we can get very nice, high quality, let's say gallium arsenide films that also have smooth surfaces. And we can actually see whether or not there are any anti-phase domains leading to dislocations in this material, even by doing an AFM scan. And then to improve the material quality further, we do other things. For example, we take that initial gallium arsenide buffer and we subject it to what we call thermal cycle annealing, increase the temperature, cycle the temperature between 350 and 750 degrees. In this case, that sort of forces some of those dislocations to move around. In some cases, they run into each other and annihilate, and we can improve the material quality. Then we incorporate strained layer superlattices. Sometimes this is in-gas-gas or other materials, because those defects also get sort of steered around because of the strain fields around these superlattices, and are forced to annihilate and mitigate. And then what you see here is what looks like very high quality material on top of a nominally sort of defective buffer that was grown on silicon, and the material quality improves as we do all this, and the dislocation density comes down to a level that is acceptable for making a fairly reliable device. And there's an example where we actually grew quantum dots on top of this buffer for initial evaluation. I think 7 layers of indium arsenide quantum dots. And this was all done by MOCVD. Here's an example, very uniform quantum dots grown by MOCVD on silicon, and photoluminescence emission at 2 different pump powers. And what you're seeing here is a comparison of the photoluminescence emission on this buffer grown on silicon compared to the same quantum dot stack grown on the native gallium arsenide substrate. The PL intensity is about the same. The full width half max is about the same. There's just a slight wavelength shift. These quantum dots look very good, and the emission characteristics are good, sort of proving to ourselves that, hey, maybe these quantum dots are very robust to somewhat defective material. Take a step back just to show the quantum dot laser performance on native gallium arsenide. Early on in this work, we had to prove to ourselves and to the community that we can indeed do this by MOCVD. You just have to use the right metal organic sources and dial in your growth parameters. And I would say these are, competitive with record-performing quantum dots grown by MBE, by other research groups, by companies. We might be the only company, university really doing this by MOCVD. And I'll skip some of the details, but you see, very good high temperature operation and attractive spectral characteristics. We also aged these lasers to show that they are reliable. They didn't really age at lower temperatures, so we had to increase the temperature to about 60 degrees. And then we start to see a little bit of degradation in the threshold current. So you extrapolate a lifetime, many years. These would pass very stringent qualification requirements for telecom, datacom, and other applications. And then after we dialed in the quantum dot growth on native substrates, said, okay, let's grow these on our gallium arsenide on silicon buffers. The only thing we did a little different, and we started to use indium gallium phosphide for the upper cladding instead of outgas, because we can grow this at lower temperature and preserve the morphology of these quantum dots. But it turned out that the quality of that in-gap wasn't as good, so the p-type conductivity wasn't as good as it should have been. So it needs a little bit more optimization, which is why you see a little bit of a difference in performance in CW versus pulsed operation. We need to reduce the resistance of these lasers, but nevertheless, working very well, putting out tens of milliwatts, fairly low threshold current, and when you extract material parameters, material gain and spectral characteristics look very good for these lasers that were realized on silicon. So let me switch gears and talk a little bit about how to scale, how to process integrate. Everything I showed so far was, hey, we can grow these materials on planar substrates, on planar silicon, and demonstrate things like lasers. But if we're really trying to get these into CMOS processes like CMOS silicon photonics, how do we do that? One way you do that is by doing selective area growth. So the main motivation for selective area growth in this case was for process integration. If we're going to take a silicon photonics wafer sort of mid-process and form recesses, expose maybe the silicon substrate or the SOI layer where we'd like to integrate gain, we'd like to be able to grow selectively, deposit the materials just in that recess and not everywhere else on like the high quality oxide that sort of encapsulated all the other components. But there are other benefits to selective area growth. For example, lots of things change when you do selective growth as opposed to sort of planar growth on a substrate. Thermal stress is reduced significantly. Instead of growing this material that's thermally mismatched with the substrate across the entire substrate, we're only depositing these material in recesses. And there's a fill factor, so a certain density associated with that. And that prevents film cracking. When we grow the films on a planar substrate, sure, we get really nice results, very good working lasers, but occasionally the film cracks. It can only grow maybe 2 or 3 microns, and that's not enough for lasers. So when we do that on planar substrates, well, when we do selective growth, in some cases we've grown 10, 15 micron films. Not that that's needed, but 10, 15 microns without seeing any film cracking versus let's say 2 or 3 microns on a planar substrate. And there's lots of other benefits to selective growth. For example, aspect ratio trapping. You can use the fact that you're growing selectively to trap some of the defects that generate when you're doing growth on planar substrates. So I'm going to go a little bit quick through this section in the interest of time, but we initially just had to dial in growth parameters to do selective growth. We were able to grow anti-phase boundary free 3,5 material, gallium arsenide and indium phosphide, in recesses right on a 001 surface that had never been done before. Usually you've got to use a miscut substrate or do something to the surface like those nano V grooves that I showed before. But we were able to grow very high quality anti-phase boundary free gallium arsenide buffers with extremely smooth top surfaces. You see a little bit of faceting near the edge because of how the growth sort of proceeds in this corner, because the fab of these recesses is not perfect, but really high quality material. And it took quite a bit of work to sort of dial in the fab and growth parameters to get to that point. You could also put the V grooves down in the recess, and we did that, and that opened up the window a little bit. Not only is the material quality better, but we could grow high quality anti-phase boundary free material in wider recesses. So instead of say 15 microns wide in the previous approach, 25 microns, 100 microns wide. So if your device is large, like a laser diode, and you need to etch a ridge and put metal contacts down, it'd be better to be able to widen that recess a little bit beyond, say, the 15 microns that was demonstrated in the previous slide. And so we grew buffers selectively, not only just gallium arsenide, but we incorporated things like thermal cycle annealing and strained layer superlattices to get the higher material quality on the flat bottom and on the recesses with V grooves down there. And you can see that the material quality gets better when V grooves are down in the recess. And just to see how good it was and convince ourselves that we could grow laser quality material, we just grew micro disc lasers that don't require full cladding or doping on both of those platforms. And just to summarize in the interest of time, these are optically pumped lasing, and the lasing threshold was a lot lower when we had the V grooves down in the recess. So where do we go from there? We've been working in collaboration with John Bauer's group at UCSB, with RF SUNY AIM Photonics and some others, to bring this into the silicon photonics platform. And this particular example here, we used MOCVD growth to grow the initial buffer, but then passed some of these samples to the MBE team to grow the quantum dots because it's a little bit more mature to grow the dots by MBE. So hybrid MOCVD buffers and maybe even the lower cladding, and then grow the dots in the upper cladding by MBE, and then go and fabricate these devices. And you can see some really nice pictures of these devices. One of the issues is that when you switch to MBE, you end up putting polycrystalline material across the entire wafer. So the wafer is going to need some cleanup. That's what I meant when I said selective growth allows you to enable process integration. If we could grow the whole thing by MOCVD just in the recess, you wouldn't be contaminating the rest of the wafer. The other issue is that near the interface, near the edge of that recess, there's a lot of polycrystalline material that actually has to be removed after the growth. So in this case, there was sort of an air gap between the 3.5 waveguide and the silicon nitride waveguide. You could fill that with a slightly higher index material instead of just leaving air there, and demonstrate good working lasers. So some recent results presented at the OFC conference and reported in this paper that just came out, very high quality MOCVD, MBE hybrid quantum dots that are operating at very high temperature and also have very reasonable lifetimes, as much as 6.2 years for this batch of 13 lasers and a mean of about 2.3-year lifetime. That was at an elevated temperature. I don't remember exactly what temperature. It might have been at best 60 degrees, but could have been 30 degrees. Refer you to the paper. And a few more results here just showing characterization of the coupling efficiency. So again, when you've got this sort of air gap, even if you fill it with BCB, the light is diverging significantly. So we'd really like to close that up. So we're able to characterize the coupling efficiency. Loss is about 5.4 dB. That's not so bad. And John's group was even able to demonstrate some fairly sophisticated lasers with DBR mirrors in the silicon nitride, ring resonators and DBRs on the drop port. So, you know, sort of single longitudinal mode lasers with reasonable side mode suppression ratio. So why do we want to do this all by MOCVD in the future? Well, look what happens when we grow the structure selectively by MOCVD. There is no gap. There's a little bit of faceting, but you have a high quality 3.5 material, conformal, butted up right against the interface. The silicon nitride is buried in the oxide here. The material has a little bit of faceting here. So you could either remove that, but it's really only a micron or so of material. So that would be a small gap and just fill that with oxide, or just leave it there. After all, it is very high index material. And if you look at simulations, that faceting doesn't do so much. Whether you remove the material and fill with SiO2, and you only have, let's say, a micron gap, you can get very high coupling efficiency, or just leave it there. And even with the faceting and sort of maybe a little bit of redirection of the light, very high coupling efficiency can be achieved. So that's sort of where we're going in pursuing all MOCVD selectively grown quantum dot lasers in silicon photonics. Don't have too much time. So let me just say something about scaling and commercialization opportunities. Illuma is a company we spun up about 4 years ago that can do MOCVD growth on very large diameter wafers. So one of the breakthroughs was to build indium gallium arsenide-based shortwave infrared detectors on large diameter wafers up to 300 millimeter silicon. In many applications, 200 millimeter is just fine. That's a picture of the world's first indium phosphide on silicon 300 millimeter wafer. You can see that it's very, very shiny, reasonable quality material that we demonstrated a few years ago. And we've been leveraging this technique and capability to build devices, photodetector arrays, large area detectors that meet very stringent performance requirements for a number of applications. And this technology is broadly applicable, even just as a sensor, in lots of things, in mobile, consumer, automotive. And if you expand and think about quantum dot lasers and quantum photonics and even 3.5 on silicon electronics, you can leverage this technology for a wide variety of applications. So that's the breakthrough, being able to deposit these 3.5 materials, not just on small substrates like we've always done, even if it were silicon at the university, but even being able to bring that to 200 millimeter and 300 millimeter substrates. And why might you want to do that? Well, it's really for scaling. And it's not just scaling for volume, like many more chips per wafer because you have a larger wafer, but it's about getting access to that highly automated manufacturing environment that you have in the silicon world, and being able to do monolithic integration with CMOS, and being able to do wafer scale integration and packaging. A lot of the wafer scale integration and packaging that we hear about in the news now only happens on 200 millimeter and 300 millimeter substrates. So Illuma is doing this, has a facility nearby UCSB with some clean room environments, houses a 300 millimeter production scale MOCVD capability, but can grow on any substrate size from 2-inch up to 300 millimeter. Illuma is a proud user of the UCSB Nanofab that I mentioned earlier, and has lots of partners for scaling, especially for fab, but even for scaling the epi to beyond what the company can handle. That gives sort of a summary of the technology or product offerings that include detector arrays, large area detectors, now quantum dot lasers, quantum photonics, and even nanoscale semiconductors for 3.5s. Just a few pictures showing some of the detector arrays demonstrated on these large diameter substrate platforms that can be delivered for evaluation or can be assembled into focal plane arrays, large area detectors for consumer applications that are either pins, APDs, or even Geiger mode APDs. In the silicon world, people refer to those as SPADs. And Illuma is also partnering with AIM Photonics, has been for the last few years, but publicizing more, because what Illuma does is can grow those structures on the 300 millimeter wafers. And Illuma did the growth on some of those MOCVD MBE hybrid quantum dot lasers that I showed earlier. So we're now able to do this on 300 millimeter scale, not just on small wafers like we've done in the past for university level demonstrations. In addition to gain, you can also think about integrating other components. Illuma has some customers in contracts to add 3.5 materials for quantum photonics. For example, another functionality a different type of modulator material, either AlGas or indium gallium phosphide, that could be used for modulation or for entangled photon pair generation in quantum. And what's unique about Illuma's capability is that it could take that to 300 millimeter, add that layer to an SOI silicon photonics platform, and get access to very low loss waveguides, which is what you really want for quantum. And then a program that kicked off a few months ago, using this for what, you know, sort of was always the holy grail of 3.5 on silicon, nanosheet transistors in this case. And there's a collaboration with some other hub partners, UCSB and Teledyne, a little bit different than the way this was done before, using selective area growth and very aggressive forms of aspect ratio trapping that we hope to publicize exactly what we're doing there to realize very high quality defect-free films on silicon for things like HBTs that you heard about from Mark Rodwell and others in other seminars. So let me wrap up and say that MOCVD MBE hybrid approaches are very good for interim demonstrations and for low volumes. Please take a look at that paper that we published with John Bauer's team that's published in JLT now. Very excited about those results. And for those of us that working on the project, we know that there's a lot of room for improvement. So we expect to have a lot of publications in the coming months showing what we're doing, because that was really just, you know, initial demonstration. I think ideally you'd like to do this all by MOCVD. And that's what we hope to do in the future, just grow everything selectively by MOCVD and that recess. It simplifies the process integration and can make very high quality lasers. And if I look back, I can remember, you know, just talking about sort of that transition from MBE to MOCVD for commercialization and scaling. I remember a time probably almost 20 years ago when VCSELs were being commercialized mostly for communications applications. Now VCSELs have exploded for sensing applications. People were trying to figure out how to grow those DVR mirrors by MOCVD and saying, oh, this is really hard. And a lot of people were saying you can't grow VCSELs by MBE. Those of you in the field know that all commercial VCSELs are grown by MOCVD now. And some of that is because of the volume scaling that was required for consumer markets to get VCSELs in iPhones, for example. And there's lots of other examples where some of these technologies transition from MOCVD, from MBE to MOCVD. If you can grow it by MOCVD, it'll eventually go there if scaling and commercialization is required. People have told me and said that you can't grow quantum dots by MOCVD. It happened in the conference session. One of the first talks said, somebody asked the speaker that talked about MBE quantum dots, hey, can you grow quantum dots by MOCVD? And the speaker said, no, you can't do that. And then I gave a presentation just after that showing very high quality MOCVD quantum dots, and people in the room were kind of confused. So my prediction is that as the demand for quantum dot lasers and integration with silicon grows, all commercial quantum dot lasers will eventually be grown by MOCVD. Last thing, maybe I'll just leave up. If you're interested in these topics, we've got a really nice session happening at the Optica Advanced Photonics Congress, silicon photonics manufacturing, customer requirements, and fab readiness. NVIDIA is speaking there, Tower Jazz, ST Microelectronics, some other really large volume silicon photonics fab. So please consider attending this meeting to hear about what's happening in the industry. Thanks very much for your time. I'm sorry if I went a few minutes over, but happy to take any questions if we've got time.
Thank you, Jonathan. Timing was good. We do have time for questions. I will have one if somebody else doesn't, but I'd like to get somebody else in. Okay, I'm going to start with a possibly self-serving question. The UCSB Nanofab has had so much success in tech transition. You gave a lot of examples of that. But I wonder if you could take a step back and talk a little bit about why you think that's true, and then what you think the California Dreams Hub could do to enhance the model that you've been so successful with so far.
Great question, Steve. Thank you. I think one of the reasons, sorry, I think one of the reasons we've had a lot of successes, lab to fab demonstrations, and some of those went to industrial fabs for commercialization. Some went to some of the hub partners that we have, like Teledyne and Northrop and HRL and others. Part of that is because we've always had a very strong collaboration between materials research groups and device research groups at UCSB, and also some very good circuit designers. I think that has something to do with it, because when you get a nice mix of people that are not just developing the materials for the science aspects, but really trying to develop materials for a device, and you've got circuit experts thinking about the application, there's sort of a natural transition to go commercialize things. And so I think that's a major factor. And one thing that I'm really excited about, which we've been building out in California Dreams, is the fact that we've now got an even bigger mix of not only compound semiconductor materials, device, and circuit experts, but also silicon experts. And we've got Moses and Moses 2.0 in the mix. And various of our partners, not just us, but Sandia and others, are trying to bring 3.5s into Moses. So I think that's really going to open things up. The fact that you've got sort of the entire ecosystem, customers at the far end, Moses that could be a storefront and figure out how to broker all the requests, everything in between, all the way down to, hey, there's a customer that wants to work with our nanofabs through the hub to just develop a new etch process module for something. We've got the whole gamut now as a hub. And there's lots of examples that we can discuss, not just historically, but things are happening right now within our hub. So I think we are in a really good position to sort of build that model out and expand out into other parts of the ecosystem, packaging and prototyping that we haven't traditionally done.
Thank you. That was very helpful. I'll also add that you talked about the collaborations in your lab, and that's very important. And that extends to the staff supporting your lab and the culture surrounding the lab between the faculty and
Yes.
students and staff. A great team to work with, and it's clear what an impact that has, and that it's not just a collection of equipment.
Yes, thanks for pointing that out, Steve.
Sure. I see a hand up from Priya.
Yes, hello. Hi, Professor Klamkin. Agree with everything Steve said. And as HPE, we have a close relationship with the UCSB clean room as well. My question was the result that you showed with ALUMA and with growing indium phosphide and silicon and other 3.5s is very impressive. And, being able to scale to that large of a wafer is best of both worlds. So my question is, do you have any comments on your thoughts on singulation? Are you able to use the same singulation methods as the silicon CMOS world uses, or is it more the 3.5 approach? Or if you had any comments on that in terms of getting from that integrated wafer to the die form?
I think I understood the question. Are you talking about singulation, like to expose waveguide facets, or?
So once you have the indium phosphide integrated onto 300 mm, I'm just wondering how you get from the wafer form to die.
Oh, I mean, just standard dicing. I can give a little bit of background. Some of the demonstrations we did, materials growth actually happened on the 300 millimeter wafers, because some of those wafers go through part of the fab at AIM Photonics. Recesses are formed to expose and partially etch into the silicon, and then the wafers make it to the partners to do the initial nucleation and buffer growth. A lot of that growth happens on the 300 millimeter scale. Even the quantum dot growth with IQE as a partner. But sometimes what we do is cut the wafer into die, maybe to do the final growth of the dots at UCSB instead of at IQE. And then most of the fab demonstrations for lasers, die coupons were diced in order to do the 3.5 fab at the UCSB clean room. And so all the lasing results that you see were carried out that way. in parallel, AIM has been developing out all the 3.5 process at 300 millimeter scale. And it's getting close to being ready. Most of the steps are there. There's a few things to tweak, but a lot of what's happening now is just moving away from doing stuff on small pieces and doing it all at the 300 millimeter scale. So imagine Illuma doing the buffer growth and maybe the lower cladding, and then IQE doing the quantum dot growth, and then all the fab happening at AIM Photonics. And our hope is one day Illuma does the entire laser growth. But at the end, those wafers go back into the fab, and it's almost like they're any silicon photonics wafer. The gain structures are integrated. They're completely buried in the oxide, just like a germanium detector or something else. They sit below a few of the metal interconnect layers, and the wafers just get diced in most cases at SUNY's TAP facility up in Rochester.
Okay, well, thank you so much. I
Yeah.
appreciate the insights.
Thank you.
Thank you for the good question, Priya. We're past the end of the hour. If there's one more quick question, I'll take it, but I don't see any hands up. We have positive comments, but not questions in the chat window. So thank you, Jonathan, again, for such a great seminar. And as we finish up here, I will just remind people that we have more great seminars coming up. Next week, Hamid Reza Agassi from UC Irvine. The week after that, we have Steve Zamek from PDF Solutions, along with Jonathan's colleague from UCSB, Brian Thibault, speaking of the excellent team that supports the Nanofab lab there at UCSB, Jonathan Hacker at Teledyne. And then we are very lucky to have Subbu Iyer, who recently returned from leading the NAPMP program at the Department of Commerce from UCLA. And interestingly and coincidentally, we have 2 in a row from UCLA. The week after that, Chi-Wei Wang also from UCLA. So please visit our sites and sign up for the series. Make sure you get the notifications, and check out the YouTube videos for any seminars you miss. Thank you, everybody. Thanks again, Jonathan.
Thanks, Steve. Thanks, everyone.